That is definitely a smudge here, so it's, as a matter of fact, testing fundamentally the earliest structures we know in the universe. This sort of information is provided in a small portion of the time that we were previously able to, so I think a ton of the records that we have in the current-day universe will truly be broken before long. A notable Nobel Prize winner says that the James Webb Telescope has recently discovered something unusual in the universe, and the changes that are coming may not actually be ready for us. The most recent discoveries are extremely concerning for science, as an increasing number of strange things are happening. Since James Webb has detected a brand new phenomenon that is turning our physics books on their heads, Adam Rees, an astronomer and Nobel Prize winner, has long thought that science is on the verge of crisis. There are heaps of strange issues that are getting more significant every day, according to experts. Can we still figure out what's going on, or is the field of science over? Adam Rees is likely one of the few experts who is staying calm these days. Things are not the same as they were before the James Webb Space Telescope was launched. It's becoming increasingly clear that the universe is much older than we thought, galaxies have formed much faster, and in completely different ways than we assumed. The universe may not be expanding from a single point. What should we do now if dark matter was just a mistake and the James Webb Telescope is now showing us a new picture of strange occurrences in the universe? One of the most knowledgeable individuals in the field of studying the universe's expansion is Adam Rees. His work on observing that the universe is expanding faster than we originally thought impacted how we think about the cosmos and was a huge part of the Hubble excitement. Having worked hard for years, Rees knows that our understanding of the universe is flawed. He is excited about what the telescope has found recently. He has helped look at the universe and used supernovae as standard candles for the first time. Researchers use cosmic scales to measure how far things move and how fast they move. Lights are a ton like those utilizing supernovae as a standard. Estimations were incredibly precise, yet there was still one issue. Rees and his group found that the universe was growing in certain areas more than others, which was not what they had expected. During their work, something else became clear. Rees's estimations were altogether different from those based on the redshift method, which shouldn't have been the case. The Hubble tension is what we presently call these differences in the estimations. Their work was so amazing that Rees, alongside his associates Saul Perlmutter and Brian Schmidt, won the Nobel Prize in Physics in 2011. It turns out that he won the honor for discovering that the universe is expanding faster than expected. Schmidt and Rees are both part of its Great Z Supernova Search Group, which is investigating ways to improve distance measurements in the universe as part of the Supernova Cosmology Project. Perlmutter, on the other hand, came to similar results around the same time. They observed Type Ia supernovae, which are very bright stars that explode and serve as a reliable way to determine distances in the universe. These findings surprised everyone by showing that the rate of expansion of the universe is increasing rather than decreasing, as had been previously thought due to the gravitational pull of matter in the universe. The idea of an isotropic universe was a problematic notion. It was becoming the most serious issue in modern science, and now it has emerged that, these days, scientists and cosmologists are continually facing new questions and surprising facts. The concept of an isotropic universe is also beginning to unravel, taking with it one of the most significant aspects of our universe. Regardless of what direction you look at the universe from, isotropy suggests it appears the same. A key part of the cosmological principle says that if we look at the universe on a large enough scale, it is uniform and has similar regions. For example, the pattern of cosmic microwave background radiation appears similar everywhere. Additionally, large groups of galaxies are spread evenly in space, or at least, that's how it appeared in the past. Researchers then turn these observations into simple mathematical rules to make the world easier to understand, but this may have been a very misguided notion. Adam Rees and other researchers studying accelerated expansion initially demonstrated the isotropic model, at least in part, because supernova measurements showed that the rate of expansion is generally the same. It seems there is some sort of isotropy. However, the expansion is occurring much faster than traditional physics would predict. Dark energy is still a highly intriguing topic. Right now, we need to learn more about dark energy to solve the puzzle of new cosmology. We still don't fully understand what this energy is made of, but knowing it exists and what it does is crucial for understanding how and why the universe expands in a way that isn't skewed and how the current standard model of cosmology came to be. Dark energy is thought to be a form of energy that could exist throughout the universe. It is likely a key part of the current theory of cosmic expansion, being the force thought to push against gravity and accelerate the universe's growth. It spreads out the universe according to current cosmological ideas. Dark energy makes up about 68% of all energy in the universe. This presents a problem. Scientists say that an energy that has never been proven to exist is responsible for almost 70% of the energy processes in the cosmos. Observations of Type 1a supernovae by Adam Rees and his colleagues were crucial evidence for the existence and properties of dark energy. Until recently, the rapid expansion observed couldn't be explained without a strong force pushing against it. The cosmic microwave background radiation and other large-scale structural analyses have shown that this mysterious energy is quite real, though new discoveries made by the James Webb Space Telescope has made individuals question the possibility of dark energy. The JWST can observe the early universe with more precision than was previously possible. The standard model of cosmology suggests that structures and objects should be younger and less developed than they were when the first detailed observations were made. It's possible that these findings indicate that the universe may have started earlier or expanded much faster than previously thought. These discoveries suggest that we still don't fully understand some significant astronomical components and forces, like dark matter and dark energy. This could imply that the current model of the universe might need to be completely reconsidered. However, we can't formulate new theories yet because we don't know enough about what's going on. Will the universe of quarks hold the answer? We might have to wait a bit longer for a shift in how we view the cosmos. We won't be able to piece together a new picture until JWST sends more images and scientists uncover even more astonishing findings. It could take some time. For now, experts around the world are searching for solutions that are evolving. David Gross, another scientist, views this as an exciting problem and an opportunity. Gross says that the answers to the universe's big questions are not hidden in the big picture but in the small picture. Gross, a notable theoretical physicist with extensive knowledge of string theory and strong force interactions, won a Nobel Prize in 2004 for discovering asymptotic freedom in the theory of strong interactions, a critical finding for understanding quark behavior. Quarks are the building blocks of protons and neutrons. The standard model of particle physics is based on these particles, which form the building blocks of everything we can see and measure in space. Because of this, the fundamental structures and rules of the universe should also exist in the subatomic world. Gross helped to develop ideas about what happened just after the Big Bang. Back then, there were no stars or other objects. For hundreds of thousands of years, there was only an extremely hot primordial soup where particles could move around without sticking together. Before the Big Bang, there may have been only a type of quantum fluctuation where all forms canceled each other out, making them effectively zero. This quantum state broke down with the Big Bang, releasing particles filled with charges and forces into a space that didn't exist before. Eventually, these pieces formed galaxies, planets, stars, and life. Should we believe Gross when he says that these particles hold all the answers? Most likely. But how can we study how particles behaved 13.8 billion years ago? One tool scientists use is the microwave background radiation from space, thought to be an excellent record of what happened shortly after the Big Bang and likely unchanged since then. Quantum physicists and classical physicists disagree on how to interpret this record of the early universe. Quantum physics and particle physics cannot be fully aligned with standard cosmology. Quantum physics doesn't agree with what we know about created matter, or rather, the missing link is quantum mechanics. David Gross is confident that this connection can be found in particles and forces we know very little about. He has worked tirelessly to bridge quantum physics and general relativity so they make sense together. Gross's work on asymptotic freedom demonstrates how particles behave when their energies are very high, which is crucial for understanding the early universe just after the Big Bang when energies were extremely high. His ideas could help us understand parts of the universe's evolution that we don't yet fully comprehend. However, there is some disagreement among scientists. Many traditional physicists believe that string theory's ideas are too difficult to accept. David Gross thinks that quantum fluctuations in the cosmic microwave background hold answers to the unresolved questions. The cosmic microwave background, CMB, can be observed everywhere on Earth. From 1989 to 1993, the Cosmic Background Explorer, COBE, satellite was in orbit. It was the first to detect tiny temperature fluctuations in the radiation. The Wilkinson Microwave Anisotropy Probe, WMAP, examined these changes from 2001 to 2010 to determine if they indicated evidence of the Big Bang. The Planck satellite recently created one of the most detailed maps of the CMB. Scientists are still unsure how to interpret this data. Some researchers claim they have found proof of the Big Bang in the CMB, while others believe it reveals collisions with other universes and evidence of a multiverse. Join us now and be a part of every new discovery in our upcoming videos.